I'm Tobias Fiebig, and I'm presenting the work I did together with my colleague Jan Chrysler, probably better known as Starbuck, and, and our colleague from the computer vision department, Ronny Hensch. So we have been investigating high-resolution cameras in smartphones, and what you probably notice is that nowadays, these resolutions get kind of bigger. So that was, kind of the first strike why we got into this. Next thing is, if you look at these all fancy new technologies that, try to separate different compartments. One compartment the user can, do whatever user likes, install malware, all the stuffy Candy Crush and so on. And one where it's the actual serious business going on, it's pretty hard to actually have intercompartment communication. So basically what you would like to is, if you have owned the public compartment, to get stuff done in the confidential compartment. Why we chose a camera? So apparently, following work by Feld et al., it is considerably easy to get camera permission from a user. Well, for once, basically, because users just click, accept, install, I just want to use it now. And the other thing is that the camera permission is actually one of the most, over-requested, so it means requested, although not used, permissions in the Android market. So, summarizing our contribution, so we demonstrate that the front camera of modern smartphones can be utilized to apply the approach of Xu et al. To perform keylogging operations, and that should have higher precision than previously presented camera-based keylogging operations by Simon Anderson. We also evaluate the required border conditions, so we basically can tell you which resolutions make what big size of a problem. And we demonstrate that an attacker can actually utilize the other side camera, that means back camera, to steal a target's fingerprints for subsequent later use. So let's first dive into the development of cameras. So what you can see here is a small graph of data obtained from GSM Arena, demonstrating the development of smartphone camera resolutions on the back side. And you can basically see nowadays there's basically no smartphone without a camera anymore. And the average resolution for the back camera is above 5 megapixels. If you look at the front camera, you see a kind of similar development, which only lags a few years behind. So our estimate is that the front camera is around 6 years behind the back camera. But by now, even more widely deployed, and you even can see the first really high-resolution front cameras. So why does this happen? So first thing why it certainly happens is because we don't want to carry around a lot of cameras with us when we're going around. But if we now have one camera on our phone, we certainly don't want the pictures taken with that phone to look like this. That basically explains why we have a high-resolution camera in the back, but it certainly doesn't explain why you have one in the front. And for the front, there's a simple explanation. Well, serious video conferencing, or something like that. So, quickly go through the attacker model. We have to have somebody with a lot of resources, a lot of knowledge on computers, and that person has to be attacking high-profile targets. So, thinking about that, we didn't really get any idea who it might be. But well, I think we'll figure out someday. Talking about our victim, we have to have somebody who's interesting enough for that attacker to be attacked. And they probably use some kind of secure phone, because else, well, our attacker would, don't have to use techniques like this. And they have to be kind of well known. So we've been thinking really hard, but I guess we found our victim. So let's briefly go into keylogging with the front camera. So how we do it? So we use reflections in the user's face. And if you think about reflections, ideally you have sunglasses on. That's pretty nice for San Diego. However, if you don't have sunglasses, you can just use the eyes. And it basically works like Xu et al. Did it in their 2013 CCS paper. So what they did there, they used the reflections, for example, in users' eyes or in sunglasses, recorded with some high-profile equipment they had to bring close to the target, which we don't have to do because our victim is buying the camera for us. So from this work, we can learn that they basically had perfect reconstruction on input based on the movement and the shadow of thumbs if the size of the display in the recorded reflection was around 10 pixels in height. And, oops, they even left us a nice formula with which we can calculate based on the camera, based on the distance, based on the initial object size, how big our reflection will be. So doing this, we get to this nice graph. This red line here indicates this 10-pixel boundary Xu et al. Had to use for perfect reconstruction. The upper line is for phones held 30 centimeters away from your face, a pretty, relatively uncommon thing to have it that close to your face. And the bottom line here is for 60 centimeters, which is also pretty uncommon. So with that, we can say that on 30 centimeters, we might even have luck with the 2-megapixel cameras randomly found in every average phone which is on the market right now. If the phone moves farther away, then we have even better success. Then we need even higher resolution cameras. So the biggest thing we found on the market today is a 13-megapixel camera in a China-based Oppo phone, also known as the cyanogenmod phone. It's a turnable camera, so it doesn't really count, but it's basically the best we could get our hands on. So let's quickly do some keylogging. So this is what the user does. This is in the eye. And we all watch CSI, so this is what happens if you zoom in. But then we can start, to draw on that picture, for example, the sump we saw. And then we can utilize a little layover of the keyboard used. And then it becomes kind of clear how this all ended up. So we covered eyes now, but we also have to investigate what happens if our target wears sunglasses. And these sunglasses here are not the ideal case for us. Actually, what we want are sunglasses like these. So this is actually our former Secretary of Defense in Germany. He also had some kind of PhD, and now he has neither. Apparently happens if you start copying other people's work and stuff. So with that, we can actually calculate how big, how big a single key of a keyboard, of a QWERTY keyboard, will be in our reflection if the target has, like these high reflecting sunglasses. And the interesting thing is that somewhere here between 16 and 32 megapixels, the key, the single key in the reflection actually becomes, 10 pixels high, so probably distinguishable. So looking at what we see if the target wears sunglasses is this. So you can see the input field, and you can even distinguish the single keys of the keypad. Let's briefly talk about mitigation for this before we dive into the next part of the topic. So you could use viewport filters, privacy filters. However, privacy filters have this little issue that they let light through in the direction of your eyes because you're supposed to see something, which is not exactly helpful with our approach. You could start to randomize keyboards, but if you introduce randomized keyboards, you're probably seeing your users with torches going after you. You could have gaze-based passwords, which are using the camera as an input for the password, which does not work as well. So basically what Samsung and Apple came up with is biometric authentication. So let's see what we can do with that. So we talked about the issues that arise from the front camera, talking about the back camera now, and biometry being kind of a thing, especially to secure high-value assets. We came across this situation. I think everybody knows it. If your phone is on the table, you basically want to get it again somewhere, then grab for it, And well, at one point, your fingerprint is kind of right in the picture. So we actually try to figure out what that gives us, and that's actually processes give us. So we can extract the image, binarize it, put it on a PCB. Well, if we want to get around the S5 or 5S, we have to apply graphite to adjust the capacity of the wood glue. We then subsequently peel it off, and we have a forgery. In a quality sufficient to do the 5S, S5, and stationary fingerprint readers. So what can we do with the target's fingerprints? Well, we can certainly circumvent access controls, unlock iPhones, which is fun, especially at places where iPhones tend to lay around. And we can plant false fingerprints somewhere. And that's somewhat disturbing, because last time I heard, officer, no clue how my fingerprints got on that knife, did not work out in court. So please don't try that. And the last thing we could do, just kind of a little shaky, you could try to actually track users across devices by reading their fingerprints, but basically there are better techniques to track users based on behavior, browser stuffy. So concluding on this, front cameras in smartphones make actually good keyloggers. Back cameras can be used to extract biometric information, and mitigation is hard. So we really banged our heads what we could do to mitigate. Basically, the only thing we came up with is this. However, there's that non-existing company from Finland, which actually had a somewhat better mitigation, which is this. So they actually bring, I don't know if you can see that, they actually bring a lid you can use to close your camera, which does not require you to glue something like duct tape on your camera, which is sticky. So maybe vendors should think about having that again, because that's useful. And if that's said, it works. So thank you again. These are my references. Any questions?
A possible mitigation that I didn't see listed, there's usually a light that will come on to indicate that the camera is recording. Are there a lot of ways to bypass that, or are vendors no longer using that technology?
So in mobile phones, you actually don't really have that camera light. And for notebook computers and stuff, so there's this presentation on the main conference called ICU, where it's actually demonstrated that, well, these lights are in software. And, well, software.
So I guess as an alternative to a physical cover, is there any reason they couldn't actually use a hardware light or even a shutter sound that displayed every time you take a picture?
I can only speculate why there's no hardware light or hardware shutter, but my basic gut feeling, knowing the industry, is that it would be more costly.
Pictures of heads of state on the slides, stuff is getting real stuff. All right. Yes.
Short remark. It is the hardware shutter sound, for example, was required in Japan for a long time on phones.
Yeah.
And the lobby, the phone maker lobby, actually because the price rose by like a fraction of a cent for that sound module, they lobbied hard enough. They invested like hundreds of thousands of dollars in lobby work in Japan to kick this law. So like the suspicion that it's price question is more likely correct.
Well,
It's annoying. Some users don't like it.
Like the ones that you upstairs, yes.
Well, and as you said, there's certainly no reason to assume that Japan doesn't have a threat model for this,
Yes.
even before this research. So, no other questions?